Welcome back, class. So today we are going to continue looking at Chapter 6 in our exploration of gases. And today we're going to talk about gas equations that allow us to work with when we change one of our variables like pressure, temperature, or volume. So whereas the ideal gas law allowed us to look at a situation and calculate a missing variable, what these calculations that we're going to look at today allow us to say, what if we change one of these variables? How does that work? So first we're going to look at some equations that stem from the simple gas laws that we looked at earlier in the chapter. So if we remember, we looked at Boyle's law, and remember, Boyle's law said that pressure times volume equals a constant as long as we have a constant T and N. So if P times V is a constant, that means multiple situations of P and V must be equal to each other. So if I have P1 times V1, that's going to be a constant, and P2 times V2 is going to be that same constant. So that means P times V is equal to another situation of P times V for the same scenario, if you will. So let's try an equation here. So a sample of a gas in a cylinder with a movable piston, right? So the volume can change, has an initial volume of 13.9 liters and at a pressure of 1.22 atmospheres. And we want to know, what is the pressure now if the volume is compressed to 10.3 liters? So we took our initial P, right, is 13 point, our initial P is 1.22 atm. Our initial V is equal to 13.9 liters. Our final P is what we're trying to calculate, and our final V is 10.3 liters. So if I go with my equation and I solve for P2 here, we get P2 is equal to P1 times V1 over V2. So if I plug in my numbers here, I get a P1 1.22 atm times my V1 of 13.9 liters divided by my V2 of 10.3 liters. And if I work this through the three significant figures, I get 1.65 atm. Okay. And so if I follow my units, of course, my liters cancel, and of course my P2 is going to be in units of atmospheres. So, what do we notice here? So we saw that the P increased, right? It went from 1.22 to 1.65. Well, does that make sense based on what we know? Well, what did we do? Well, during the course of the problem, we decreased our volume. Now, according to what we know in Boyle's law, that should cause the pressure to go up, which is what we saw which means yes, we saw what we should have saw, so our math makes sense, right? This is a good way to check to see if we rearranged our equation correctly, right? If what we're seeing is what we would expect to see, right? So it's a good idea to be able to work with these equations both from a quantitative, actually calculate the number, and just a qualitative, right? So we know that, oh, I lowered the volume, so I should expect my pressure to go up, which indeed it did. Okay, so that's a Boyle's law equation, right? So just if we're working with pressure volume changes where the temperature and the moles stay constant. Now, our next one we're going to look at is the equation that we got out of Charles' law. So remember in Charles' law, we said that volume over temperature equaled a constant value, right? And that's because we had a direct relationship between volume and temperature. Of course, we are keeping a constant P and N. So let's look at a couple problems here. So in the first problem, we have a balloon at 12 liters at 355 Kelvin. We cool the temperature to 275 Kelvin. What does the volume end up as? Yeah. So if we think about what we have a V1 that equals 12 liters. We have a V2 that's a question mark. We have a T1 that's 355 Kelvin. We have a T2 that's 275 Kelvin. So let's write out our equation. So we're going to solve for V2. Right? So we want to isolate V2. And so we do our algebra, and V2 equals V1. We bring T2 across times T2 divided by T1. So now we can plug in our numbers. We have 12 liters times T2, that's 275 Kelvin, divided by T1, 355 Kelvin. Of course, my Kelvin cancel. So I'm going to get my V2 in liters. And if I do math, I should come up with the three significant figures, 9.3 liters. Okay? So again, we can look at this. Does it make sense that my volume went down? So I saw my volume go down. Well, what did I do? I lowered my temperature. And so according to the Charles law, I should see my volume go down, right? There's a direct. So yes, we saw the correct effect. Right? So we would have expected the volume to drop. Now, let's do one more example here. And in this one, we have a gas sample that's at 2 Celsius, 5.6 liters. We increase the volume to 5.9 liters. What would the temperature need to be? Well, once again, we have a V1 that's equal to 5.6 liters. We have a V2 that's equal to 5.9 liters. We have a T1. Now, one of the things we want to point out when we're working with any of these equations that are looking at changes, right? What sometimes we call dynamic situations, where we're changing a variable and seeing how it affects the other variable. It doesn't matter what the units are for volume, for temperature, or excuse me, for volume and for pressure, right? As long as they're consistent. But temperature does matter. The temperature has to be in Kelvin, because when we look at the gas theories that we're looking at, right, we always talk about how things are proportional to the Kelvin temperature. And so we need to change our Celsius to Kelvin, so we're going to add 273.15, so we get 275.15 for T1, and of course T2 is a question mark. So again, let's solve for my variable. So we're going to solve for T2. So if I do some math here, or do a little algebra, right, I'm going to move T2 up to this side. So I'm going to multiply both sides by T2. That's going to cancel it out here. And then to get T2 by itself, I need to bring T1 over here. And bring V1 down here. And so I get T2 equals V2 times T1 over V1. So sometimes the algebra, you just have to be careful with it. So if I go ahead and plug in my volumes, my values, I get 5.60 liters. Make sure you're getting, whoops, see, I made a mistake there. Make sure you're pulling the right value. So V2, 5.9 liters times T1, that's 275.15 Kelvin, and V1 on the bottom, 5.6 liters. And if I do my math, do my three significant figures, we should end up with 290 Kelvin to three significant figures. And again, noting the direct relationship, I increased my volume went up, so I would have expected my temperature to go up, which is indeed what happened. So I'm seeing the correct relationship here. Okay, so Charles' law. Now, we're going to introduce another relationship here, and it's one that we've alluded to quite frequently as we've gone through this. We just didn't have a simple law that talked about it, but there is another gas law equation, which is called the Gay-Lussac law, which basically talks about the idea that pressure is directly proportional to temperature. And of course, we've seen this before, right? We've talked about the fact that if I raise the temperature, that the pressure goes up, right? If I raise the temperature, the gas moves faster, creates more collisions, which creates more pressure, right? So this is not a surprising relationship. Here we're just formalizing it in an equation. And of course, we have constant volume and amount of gas here. So we're not going to allow the volume to change like we would, say, in Charles' law to keep the pressure constant. The volume is going to stay the same, so that means the pressure is going to rise. So we have a car tire here at a pressure of 30 psi at 25 Celsius, and we cool the temperature down to 0. What's the final pressure in psi? So we got P1, 30.0 psi, P2, right? That's what we're trying to find. We have T1, right? So I convert that to Kelvin, that's 298.15 Kelvin, and T2, 273.15 Kelvin. So if I solve my equation for P2, so I'm going to have P1, I'm going to bring T2 over, divided by T1. So I have 30 psi times T2, which is 273.15, divided by T1, which in this case was 298.15 Kelvin. My kelvins cancel, and I do my math, and I end up with 27.5 psi. And again, it doesn't matter what the pressure units are, as long as we're consistent. So, according to this direct relationship, right, since I decreased the temperature, I would expect the pressure to also decrease. And again, that is exactly what I see. Now, for those of you maybe wondering, this is what's responsible for, if you've ever had the experience of coming out in the morning on a really cold winter morning where the temperature has dropped during the night, and you notice that you either can visibly see your tire looks a little flat, or maybe you get a low temperature sensor, right? What that's most likely a result of is this phenomenon here. It's not that your tires are leaking, right? You're not losing air. You're just cooling that air down so much that the pressure drops, right, inside the tire. Okay, so these are three laws where we can look at the relationship between two variables, right? Whether it's pressure and volume, volume and temperature, pressure and temperature, and see how that interaction works. But what if we want to change two variables? How do we do that? Well, the simple thing is kind of like we do with the ideal gas law. We put all of these equations together. So we put our Boyle's law, our Charles law, and our Gilles-Suk law together, and we end up with one big equation that says P times V divided by T equals P times V divided by T. And this is what we call the combined gas law. And of course, what we are assuming here is that we're not changing the amount of gas. So we're not losing or gaining gas here. But in this way, we can look at the change of multiple variables and see how it affects a third one. So let's say that I have 150 milliliters of gas at 22 Celsius, 730 millimeters of mercury, and I want to know what the volume is at 0 degrees Celsius and 760. So let's look at my variables. My P1 equals 730 millimeters of mercury. My V1 equals, equals 150 milliliters, and my T1 equals 295.15 Kelvin. My P2 equals 760 millimeters of mercury. V2 is what I'm trying to find, and T2 equals 273.15 Kelvin. So now I can rearrange my equation to isolate V2. Okay. So I'm going to have, P1 times V1 divided by T1. And then I'm going to multiply both sides by T2 to bring it over. And I'm going to divide both sides by P2 to bring it over. And I'm left with V2. So P1 V1 times T2 over T1 times P2 gives me my value. Okay, so let's plug in the numbers. So we got 730.0 millimeters of mercury times 150.0 milliliters times T2, 273.15 Kelvin, divided by T1, 295.15 Kelvin, P2, 760.0 millimeters of mercury. If I start following my units, I see millimeters of mercury cancel, I see kelvins cancel, and of course, so I'm going to get my V2 in units of milliliters. So I do out all the math, and I record my answer here to 4 significant figures, right? That's the least here. 133.3 milliliters. So, do I expect the volume to go down? Now, sometimes we can do this, and sometimes the trends go opposite each other, but let's just look at it. So what did we do? Well, we raised the pressure. Right? So the pressure went up. That we would expect, since it's an inverse relationship, we would expect the volume would go down, right? Which is what it did. Now, the other change we made was we decreased the temperature. Now, according to Charles' law, if I decrease the temperature, the direct relationship tells me that the volume should also go down. So, looks like both of these indicate that the volume should go down, which is exactly what we saw. Now, sometimes the trends will be an opposite, and it depends on which one is the biggest change, right? So, if I increase the temperature, it would cause the volume to go back up to counter this. But depending on how much I increase the temperature, you may see a decrease in the volume, you may see an increase in the volume, depending on which change was bigger, right? Which change had the biggest impact. So, but that's the combined gas law. It allows me to put all this together and look at, if I change this variable and this variable, what happens in the end, right? So now we've talked about how we can analyze all of these different dynamic changes to a gas sample. Next time, we're going to look at some of the things that we can do if we have a mixture of gases. So all up to now, we've looked at samples which were one gas, right? What if we had a mixture of gases? How does that change things? That's what we'll look at next time.